So let's look at a surface integral where we use the divergence theorem. Now, here we have, and in particular, I'm going to look at page 1113, problem 10. Now, remember the divergence theorem says this, we have some assumptions that have to be met. For one thing, we have to have a closed region. So like in this case, it's a sphere. And we have our vectors pointing outward. So it's oriented so that the vectors are going away from the surface. Think of the surface as we've got this solid, it's containing this solid, and the vectors are leaving that, pointing outward. That's what we have here. When we have that situation, we think about the divergence theorem. So we can take this surface integral and we can integrate it. So we've got this solid, and we integrate the divergence of the vector field like this. So let's see how this looks. First of all, we've got our vector field here, and I want to get the divergence of it. Okay, so here we go. We got the partial with respect to x, that's y, and it's not a vector. What am I doing? Y. Partial with respect to y, that's z. Partial with respect to z, that's going to be negative y. So here in this case, we just get z. So that's what goes in right here. Okay, so let's see what we have now. We have a triple integral. We have a z in here, and now I'm going to integrate. Now, what I'm going to integrate with respect to first, I think, is z. So I'm going to go dz, and remember, we've got this solid. You think of the sphere, and what does the sphere do? Let's just do the top part of the sphere, let's say. Okay, so if we're just looking at the top part of the sphere, z goes from 0 all the way up to the square root of a squared minus x squared minus y squared. That's what z does. So you're thinking of this top part of the sphere. That's what this is. Now, we're done with that. Let's project down to the xy plane. And let's see what we've got here. We've got a circle. Okay, and that circle is x squared plus y squared equals a squared. Oh, just replace z with 0, and there you have it. Now, I think I'm going to integrate with respect to y, and look what I've got here. I've got y equals plus or minus the square root of a squared minus x squared. So here's negative square root of a squared minus x squared, and here's positive a squared minus x squared. Okay, so there's that. And then finally, dx, and dx is going to go from negative a to a. So there's what we have to. Now, you might see this and think, well, I don't want to do this with rectangular coordinates. It's kind of awkward. I've got circular things, and I'm trying to, use rectangular coordinates. That's not good. So you might consider, well, let me change to cylindrical. Think about this. If we change to cylindrical, let's see what our integral would look like. Well, I'm going to integrate from 0 to, well, let's see what we've got here. We've got z, and let me do r dr. Okay, so I've got that. I got to remember to put r dr in there. Let's see what I'm going to integrate with respect to first. I guess I can still do the z, right? dz. I'm going to go from 0 to a squared minus a squared minus r squared, of course. I was looking at this thing right here, and it should have been a squared minus r squared. There it goes. Okay, then next, I think I want to integrate with respect to r. R is going to go from 0 to a. And then finally, I'll integrate with respect to theta, and theta is going to go from 0 to 2 pi. So this is the integral that we deal with. So this is a classic example where staying in rectangular looks mighty ugly, but converting it to polar or cylindrical makes it look a little bit more manageable. So this is what we would integrate. So if I integrate with respect to z first, let's see what I would have. Got 0 to 2 pi, and then 0 to a. And let's see here, I'm integrating with respect to z. So this is going to be 1/2 z squared r, going from 0 to the square root of a squared minus r squared. And I've still got dr d theta. Okay, so now let's see where we go now. We've got 0 to 2 pi, 0 to a, and this is going to be 1/2 a squared minus r squared times r, and then dr d theta. Okay, so we're on our way. Now we'll get ready to integrate with respect to r, but let me do this. Let me pull the 1/2 out front. We've got 0 to 2 pi, and then 0 to a. Now let's see here. We've got a squared r minus r cubed, and we're going to integrate that with respect to r. Yeah, we're almost there. Okay. So let's see what we've got. We've got 1/2 0 to 2 pi, 1/2 a squared r squared minus 1/4 r to the 4th from 0 to a d theta. Okay, now let's go ahead and move along. 0 to 2 pi. Okay, so this is going to be 1/2 a to the 4th minus 1/4 a to the 4th d theta. Okay, and of course we can simplify that a bit. This is 0 to 2 pi, and this is going to be 1/4 a to the 4th. Now, we're ready to integrate with respect to theta. Now, the temptation is to integrate with respect to a. In other words, you might say, I'm going to integrate this now. That's going to be 1/5 a to the 5th. No, no. You're integrating with respect to theta. So that's a pitfall. You can be careful, don't fall into that. Here's what we've got. We've got 1/8 outside, 0 to 2 pi, a to the 4th, d theta. Now, I could go ahead and pull that a to the 4th out while I'm at it. So I get a to the 4th over 8, the integral from 0 to 2 pi d theta. So just be very careful. You're integrating with respect to theta. You got that a in there, and it's a temptation. Anyway, so here's what we've got. We've got a to the 4th over 8 theta, 0 to 2 pi. And that, here's the grand finale, 2 pi times a to the 4th over 8, which is going to give us pi times a to the 4th over 4. And that is an example of how we would use the divergence theorem. Yeah, right there. A little bit of artwork to celebrate. There we go.